The history and future of radar technology. Radar is the invisible tech that sees everything, guiding planes through storms, mapping Earth from space, spotting asteroids, and anchoring air and missile defense. In a century, it's leaped from bulky towers to agile, software-defined arrays that steer beams in microseconds. Here's how we got from spark gap experiments to AI-enhanced sensors and what's coming next. What is radar? Radar equals radio detection and ranging. Send a radio wave, wait for the echo, measure time, angle, and frequency shift. Key outputs: range, bearing, elevation, velocity via Doppler. Core trade-offs: range versus resolution versus update rate versus stealth. ECM resistance. The first wave, 1900s, 1945, proving the concept. 1904, Christian Holzmeier's telemobiloscope shows ships can be detected by radio reflections. 1930s, national programs bloom. Britain's chain home early warning network Watson-Watt helps win the Battle of Britain. Germany fields Freya Wurzburg. The US deploys -270 Seychelles rupees. 1940. The cavity. Magnetron, Randall, and Boot supercharges microwave power, enabling compact high-resolution radars, ground mapping, H2S airborne sea search, and night fighting sets. Breakthroughs born in war. Pulse radar, lobe switching, gives monopoles, angle tracking, height finders, and proximity fuses. The transistor age, 1945 to 1980, cleaner signals, smarter detection, Doppler and MTI-MTD, coherent processing filters out ground clutter to reveal moving targets. Pulse compression chirps, long pulses for range, short pulse resolution, best of both. Track while scan and CFAR. Software tracks many targets and adapts thresholds to reduce false alarms. Weather radar arrives, from early PPI displays to national networks. The path to today's NexRad. The array age, 1980s to 2000s, point-and-shoot beams. Phased arrays, steer beams, electronically no spinning dish needed. Faster updates, multiple beams, higher reliability. PESA, active electronically scanned arrays use many transmit-receive modules for agility, low side lobes and graceful degradation. Low probability of intercept. LPI spread spectrum, frequency, agility, and clever waveforms make radars harder to detect and jam. Multifunction radar. One sensor handles air search, missile guidance, and fire control simultaneously. Precision from above. 1990s ISAR, INSAR, and dual-pole weather. Synthetic aperture radar SAR uses motion to create higher resolution images in any weather. Day-night from CSAT and ERS to Sentinel-1. TerraSAR-X, Radisat, and the upcoming NASA CISRO NISA INSAR measures millimeter-scale ground motion, volcano, inflation, earthquakes, subsidence, glacial flow. Dual polarization weather radar. Modern NexRad upgrades distinguish rain, hail, snow, even tornado debris, improving warnings and hydrology. Counter-stealth, passive and over-the-horizon, low-frequency radars. VHF-UHF systems can detect some stealth shapes at longer wavelengths with lower resolution. Multi-static and passive radar. Use separated, transmit, receive sites or existing broadcasts FM, TV to detect without emitting. OTH radar, HF skywave bounces signals off the ionosphere to see thousands of kilometers for wide area surveillance. Hardware revolutions from tubes to GaN, solid-state everything. Transistors replaced magnetrons in many roles. Digital beamforming went mainstream. GaAs gives GaN gallium nitride power amps, boost range, bandwidth and efficiency, enabling cutting-edge AESA systems on ships, aircraft and ground vehicles. Software-defined radar, reprogrammable waveforms and firmware updates extend life and add modes without new hardware. Automotive and everyday radar, 77 GHz automotive radar, adaptive cruise, collision avoidance, blind spot monitoring, now standard on many cars. 60 GHz, wave sensors, presence detection, gesture control, and smart building occupancy, privacy-friendly alternatives to cameras, drones, and UAS. Lightweight FMCW radars provide detect and void and terrain mapping. AI and cognitive radar. Machine learning enhances target classification, clutter suppression, and anomaly detection. Cognitive radar adaptive sensing. The radar learns from the scene and the jams and changes waveform beam schedule in real time to maximize information gain. STAP and next-gen processing. Space-time adaptive processing sharpens moving target detection in heavy clutter. Planetary and space radar. Planetary radar facilities like Goldstone and formerly Arecibo, image asteroids and refine orbits, radar altimetry, TOPEX, JSON and Sentinel-3, map sea level while Cryosat tracks ice thickness critical climate data. What's next? Distributed MIMO radar, networks of small cooperative sensors for resilience and better geometry, integrated sensing and communications ISAC, radars that also act as 5G, 6G nodes and vice versa, edge AI, on-array, processors for sub-millisecond detection, tracking and classification, quantum radar research. Entanglement-inspired concepts are promising, but practicality remains to be proven. If you enjoyed this article, hit the like button and tell me your ideas for my next post. Thanks for joining me. I'll see you in the next one.